Well, the next subsection that we consider in this section 5 is about assessing stability. Well, remember that if all poles lie within the unit circle, then the underlying system is stable. If there is a simple pole lying on the unit circle or a pair of complex conjugate poles lying on the unit circle, then the system is said to be marginally stable. It is at the limit of stability. If you have several poles on the unit circle or poles outside the unit circle, then the system is of course unstable. Well, if you have a system in continuous time, and we'll call it P of S, and it has a numerator B of S and a denominator A of S, you can assess stability by looking at the denominator polynomial, and then in MATLAB, of course, you can compute the roots of this polynomial to check if they are on the left side of the imaginary axis. But there is also a criterion, which is the routability criterion, which allows you to assess if this polynomial has stable roots just by considering the coefficients of this polynomial. This is something that has not been seen in last year's course of Fundamentals of Control Theory, so I have put it in the slides for your information only. So if you're given a transfer function P of Z, and we'll call it here PZ A of Z, right? What you can do, of course, is again go to MATLAB, compute the roots of the denominator polynomial and check if they are all inside the unit circle. Well, there is also another way to go, is to take this polynomial and use a so-called bilinear transformation that will transform this one in another polynomial, but now in S, right? For instance, A bar S. And such a bilinear transformation will make sure that the poles that are inside the unit circle are transformed in poles of this polynomial here that are to the left of the j omega axis, and poles of A of Z that are outside the unit circle are transformed into poles of this polynomial that are to the right of the j omega axis. And what you can then do is again use the routability criterion, right? This is also covered in the slides, but I'll leave it for your information. What I will do is, well, introduce a test on the denominator polynomial that will work directly on the coefficients of the denominator polynomial, and it's called the jury test. To apply jury stability criterion, we assume that we're given a transfer function P of Z, and we are of course interested in the denominator polynomial. We assume that A0 here is positive. If it's not, well, you multiply numerator and denominator by -1. We assume also that this last coefficient here is different from 0. If not, well, you can factor out the roots at the origin. So let us assume, for instance, that we have a denominator z cubed plus a1 z squared plus a2 z, right? And that the last one over here is a3 is equal to 0. What you can then do is rewrite this as z squared plus a1 z plus a2, and you work with this polynomial over here in the jury stability criterion. So this criterion for stability is very similar to route stability criterion. It's also applied to the denominator polynomial, but as a function of z, and it can be used to determine the number of poles outside the unit circle. To use jury stability criterion, you have to construct the so-called jury array. Okay, remember that we work with the polynomial a0zn plus a1 zn minus 1 up to an. So here you see the exponents of z and the coefficients as you see them over here. So you write them down, and just below you take the same sequence but you revert it and you write it below. So this you can construct from the denominator polynomial. Well, and then you need to construct this box over here. So the way to go is to construct this line over here. Okay, and once you have constructed, well, you take the sequence, you revert it, and you write it down in reverse order below. So these elements can be obtained using, well, these equations. So alpha n, it's simply obtained from the last column over here. It's an over a0. Okay, and this will make sure that you'll have here a 0 over here. So this one over here is obtained here. It's a0 minus this one times alpha n. This will produce this one. This one over here is a1 minus this one times alpha n. And you continue, and you will see here that, well, you would have to construct the element here as an minus a0 times alpha n, and this will produce a0 over here. So you obtain the sequence, you revert it, and you write it down below. Well, you keep on doing this until at the end, well, you're left with only two elements, right? And you continue this procedure. Okay, alpha 1 is this one divided by this one, and then you construct this one over here. It's this one minus this one times alpha 1. Okay, and then you have arrived at the end of the jury array. Once you have the jury array, it is easy to see if all the poles are inside the unit circle or not. The elements that you have to consider are the a0 I. So this one, well, this one, this one. Okay, here it's a0 0, a01, a02, and then up to a0 and minus 1. If all of them are positive, right, then the poles are all inside the unit circle. Well, furthermore, the number of a0i that are smaller than 0 correspond to the number of poles outside the unit circle. Well, let us take an example of a second order polynomial, and in here a1 and a2 are real. Okay, and we want to use jury stability criterion to see under which conditions this polynomial has roots inside the unit circle. So we have to construct the jury array. So what you see over here is the power of z squared, z1, z0. So we have the sequence, a0 is 1 here, a1, a2. We revert the sequence, and then we are ready to construct this part over here. So alpha 2 here is a2 over 1, so that is a2. This one here is simply this one, 1 minus a2 times alpha 2, so 1 minus a2 square. Over here we have a1 minus a1 times alpha 2, so a2, so this is a1 times 1 minus a2. We take this sequence, we revert it, and then we continue, right? So alpha 1 is this one here divided by this one. Okay, remember that this one here is simply 1 minus a2 times 1 plus a2. So this is the alpha 1 that we obtain. And the next one is this one over here minus this one times this one. So this is the complete jury array. Jury stability criterion tells us that this polynomial d of z has its roots inside the unit circle if and only if a01 is positive and a02 is positive. This is what we had obtained in the previous slide. This second condition can be rewritten a little bit differently. Remember again that this one is 1 minus a2 times 1 plus a2. So you can rewrite it as follows. So you obtain the two following equivalent conditions, right? And this one here can be written to be equivalent to what you see over here. So we obtained the three conditions over here. So a2 lives in between 1 and minus 1. This condition here says this is the line 1 plus a2 is equal to a1. Okay, you have to be on this side of this line. This line over here is 1 plus a2 is equal to minus a1, and you have to be on this side of the line. So you can see here that to obey these two conditions, a1 and a2 have to be inside this triangle. And if this is the case, well, the roots of this polynomial over here will be inside the unit circle. Remember from the course of last year, Fundamentals of Control Theory, that this process here has an infinite gain margin. This means that the critical gain is infinite. The critical gain is the maximum gain that you can have in your control loop, assuming a proportional controller, before you reach instability. So for this process here in continuous time, this critical gain is infinite. We will now review this situation in the case of a sampled data system. So we will have to work with the zero order Hall discrete equivalent of the process. And remember that we have computed this zero order Hall equivalent in the previous section. So the question is now, what is the critical gain as a function of Ts? You know that this zero order Hall will introduce a delay of roughly Ts over 2. So you can feel intuitively that this delay is going to make sure that there is now a finite gain margin and that there will be a critical gain that is no longer infinite. Well, let us continue with our example. The closed loop transfer function is pc over 1 plus pc, and in this case c of z is simply a proportional controller. So with this discrete time equivalent, the zero order Hall discrete time equivalent, and with this proportional controller in the loop, this closed loop transfer function can be computed and rewritten as follows. And here, of course, you do not need jury stability criterion, because you will see that this closed loop is stable if k minus 1 plus k exponential of Ts over t in absolute value is smaller than 1. Okay, so we can still have a look. We can construct the jury array. Okay, it's a first order denominator, so this is z to the power 1, z to the power 0. We take the sequence and we revert it, and then we finalize the jury array by computing alpha 1. It's this one over this one, so that's alpha 1, and this one over here that has to be positive. Well, it's a0 minus this one times alpha 1, so it's 1 minus this expression here squared, and you can see that this is of course equivalent with what you see over here. Well, this is the condition that we had found with the jury criterion test, although we didn't need it here. So this means that this expression has to be between -1 and 1. Well, only this part of the criterion will be relevant because we are working of course with a k that is positive. Okay, so a proportional controller with k positive, and this you can of course rewrite as k1 minus the exponential of tst is smaller than 1, and you take this one on the other side, so you end up with this expression over here. So here you have the critical gain, and that's k here on the y-axis, right? And here we're using ts over t, and we're plotting this expression here as a function of ts over t. And you can see here that when this ratio becomes rather small, the critical gain increases, and if ts over t tends to 0, which is really the continuous time situation, the critical gain indeed goes to infinity. Whereas when ts becomes larger and larger with respect to the main time constant here, well, this critical gain is then decreasing. This is kind of obvious, okay, because when ts is increasing with respect to the main time constant, well, the effect of the zero order hold mechanism becomes larger and larger in the analysis of the sampled data system. Next on the program is the concept of internal stability. So notice here the loop that we are considering with the set point signal. Previously we have denoted it R. The load disturbance, we had considered it as W, and dV, the output disturbance. Here N is measurement noise, right? So here in this course I should write C of Z, SP of Z, etc. But the concept here of internal stability is also valid for continuous time systems. We can write PV as a function of the different inputs SP, DL, DV, N, set point, load disturbance, output disturbance, and measurement noise. So this is how you have to read this. PV is this transfer function here acting on SP, this transfer function acting on DL, this transfer function acting on DV, and this transfer function acting on N. And then you have something similar for MV. As you can see, there are different types of transfer functions that are appearing. Okay, 1 over 1 plus BC, P over 1 plus BC, C over 1 plus BC, and PC over 1 plus BC. And you have sometimes the same transfer function but with a different sign, right? But you can see here that there are 4 types of transfer functions. And internal stability says that, well, the system is internally stable if all the transfer functions that you see over here are stable. You will see in the next 2 slides that this concept of internal stability will prevent so-called unstable pole zero cancellations. For instance, in the framework of this course, having the unstable poles of the process, for instance, cancelled by zeros in the controller that are outside the unit circle, and we'll call them, between quotes, unstable zeros. Note that you have to be able to reconstruct this transfer matrix over here and find the different transfer functions. By the way, this transfer matrix is valid in the case of a single input, single output system. I will show you again how you can find these transfer functions, and I will do it directly in the multivariable case so that these quantities will become transfer matrices, and you will see that you will have a different result than what you see over here. So this is only valid in this CISO case. Okay, so for instance, if we look at the relation between MV, okay, and SP, so this transfer function here, well, you put all the other inputs to 0, this one, and this one, and you can see here that, well, MV is C acting on SP minus PMV, right? So this is CSP minus CPMV, right? So we take this one on the other side. We have we are assuming here that we are in the multivariable case. You would have an identity matrix plus CP acting on MV is CSP, and MV is this matrix inverse. We are multiplying this equation by the inverse of this matrix over here, CSP. Okay, so in the multivariable case you would have something like this. Of course, you cannot interchange and replace CP by PC in the multivariable case. You can in the CISO case, and this is why this becomes C over 1 plus PC in the single input, single output case. Let us look at the relation between the load disturbance and PV, and again we'll do this in the multivariable case, and then we'll verify if this simplifies to this transfer function in the CISO case. Okay, so we're considering a load disturbance, so all the other inputs you can put to 0, and you obtain, well, PV is P acting on DL, right? Here you have a minus sign, minus C times PV. So we have P DL minus PC PV. We take it to the other side. We are in the multivariable case, so identity matrix plus PC acting on PV is P DL. So here PV is, well, this matrix inverse. Now we multiply this whole equation by this matrix inverse. So in the multivariable case, this is the relation that we have, and then we speak here of a transfer matrix. Notice here that the order is different than the one we had considered before. So in the CISO case, this will of course simplify to this transfer function as shown here on the slide. We'll first start with the situation in which we cancel an unstable process pole. So here we have a process that is described by this transfer function, and here you have a pole that is outside the unit circle. So indeed we have here an unstable process P of C. And we will show that it is not a good idea to cancel this pole by a 0 in the controller. Okay, if you multiply P of z and C of z, you will see that this cancels out. We'll call this an unstable between quotes 0 of C of z, because, well, an unstable 0 in itself is not a problem. Okay, it will not produce instability, but we call it unstable between quotes because the 0 is outside the unit circle. Well, if we cancel this unstable pole using a 0 in the controller, what will happen is that in the characteristic polynomial, this root will still be present and the system will therefore be unstable. So if you cancel the pole by 0 in the controller, it will disappear from the transfer function over here, but it will still be present in this transfer function over here. So there will be a cancellation here in the denominator, but there is nothing to cancel over here. So if we write this transfer function p over 1 plus bc, and by the way, that's the transfer function that takes dl, and that links dl to the output pv, we will see this immediately. So pz over 1 plus pz cz, we'll have here bz over z minus alpha a bar z, and here we'll have the cancellation, so we'll have bz a bar z, here we'll have c bar z dz, so we'll have bz, so we'll put this under the same denominator, right? So what you have here on the denominator will appear at the numerator. We'll have a bar, this is a bar z, you cannot read it anymore, but, and then dz. Here you'll have z minus alpha a bar z, so these two will cancel out, and you'll have a bar z dz plus bz c bar z. And this is indeed the characteristic polynomial that we have at the denominator, and in this transfer function, this root that is outside the unit circle is still present, so this transfer function is unstable. Okay, so you can see here that cancelling an unstable pole of the process by, between quotes, an unstable 0 in the controller will go against internal stability because this transfer function will be unstable. Next, we consider the situation where an unstable 0 of the process, this is again between quotes here, is cancelled. So we have a process P of z in which we have a so-called unstable 0. Okay, here it is, alpha in modulus is larger than 1. We have to say between quotes because this is not going to make the process P of z unstable. What we mean is that the 0 is simply outside the unit circle. So it is cancelled, this unstable between quotes 0, by an unstable pole in the controller. So if you multiply P and C, you can see that they cancel out. But again, well, even if you cancel it out in the loop gain P times C, it will remain in some of the transfer functions, and it will remain in the characteristic polynomial. Okay, so you can see that it will kind of disappear from this transfer function because it only involves P times C, right? So P times C here, cancellation, cancellation, so it disappears from this transfer function. but it will not disappear from this transfer function over here, because this unstable pole here will appear, as you can see here, at the denominator of this transfer function. So it is also forbidden to cancel a unstable zero between quotes of the process by an unstable pole of the controller, as this will also go against internal stability. As you can see, this transfer function here will be unstable, and by the way, this transfer function links, for example, well, the set point SP to the output of the controller MV. Well, in practice, if you cancel the unstable zero of the process by a pole in the controller, even this transfer function will become unstable, because, well, this process has an, between quotes, unstable zero, but you'll never be able to cancel it exactly, because, well, here you work with an estimate of alpha, which is never perfect, or this alpha might be a zero that will be work point dependent, right? So in practice, this alpha hat here, this estimate of alpha, will never be exact, so the cancellation will never be perfect. So even in this transfer function over here, well, you'll have problems, and this transfer function in practice will become unstable as well. So in your design, never cancel between quotes unstable process zeros, and never cancel unstable process poles. In this subsection, we talk about sensitivity. As you know, the process dynamics change with time, for instance, because of wear, usure in French, and because, well, we might change the working point. So sensitivity of a system, right, to variations in these process dynamics is therefore a fundamental issue, and this is what we'll study right now. One of the major benefits of working in closed loop is that this closed loop architecture mitigates, or in other words attenuates, the consequences of these process dynamics variations. Well, if you have a differentiable function f of x that maps the complex plane into the complex plane, so the input will be a complex number x and the output will also be a complex number f of x, well, then you can look at the sensitivity function, which expresses the influence of variations on x on the complex number f of x. So this sensitivity function can be written like this, and it expresses the relative variation of f of x divided by the relative variation of x. So this is the relative variation of f of x, and what you see here on the denominator is indeed the relative variation of x, and here delta x is the variation on x, and if we let this variation go to 0, well, we obtain the sensitivity function. So what you can do is rewrite this a bit differently, and if we let the variation go to 0, what you have over here is the derivative of f of x with respect to x. So the sensitivity function associated with this differentiable function f of x is the derivative of f of x with respect to x divided by f of x divided by x. Well, we'll first look at the sensitivity in open loop, and then the relevant transfer function is the loop gain process times controller. And this is, for instance, the case when you do steering or you do feed forward. So let us first consider steering. You have a process P, the output is PV over here, the input MV v. So what you could do in order for PV to follow the set point is to put over here a P minus 1, right? And this in this case will be the controller, okay? And this is called steering. Well, another thing that you can do, and it's the same idea, is feed forward. Assume that you have a process over here and you have a disturbance acting on the input, sorry, the output. So this is PV, and assume that this disturbance here is measured, right? So you've seen in last year's laboratory that, well, if you put minus d over p over here, you can reject the disturbance using feed forward. Well, then this one over here, we'll call it C feed forward, okay? But again, you see that you have the inverse of the process that is acting. So feed forward and steering are two cases where actually you're working in open loop and where the gain involves P times C, here C steering, here C feed forward, and well, in these cases you see here that C is related to the inverse of the process. Okay, so what we'll assume here is that C is fixed, okay, and we'll look at the influence of a, well, variation in P. The sensitivity in open loop can be written as follows. Okay, so you take the derivative of this one with respect to P. This is C. You divide by the loop gain divided by P, and what you see is that you have a 1 over here. And the interpretation is that any perturbation on the process is reflected entirely on the open loop gain. So this is the, well, negative side of these types of control, steering, feed forward. And this is why you always see this type of control associated with a feedback. So in addition here, what you will have is a, for instance, PI controller that will work together with the feed forward in order to reject this disturbance. So we can have a look now at the sensitivity but in closed loop, and what we'll do is consider a tracking problem. And if we consider a tracking problem, the relevant transfer function, this is the transfer function from SP to PV, is the complementary sensitivity function, and we had denoted it T, right? And this complementary sensitivity function is PC over 1 plus PC. So here we consider a tracking problem, but you could also consider a load disturbance rejection problem. Then the relevant transfer function would be the one that goes from DL to PV, okay, and the relevant transfer function would be P over 1 plus PC. But you can do the same exercise and you will see that the resulting sensitivity will be identical. I'll leave this to you as an exercise. So we can now have a look at the sensitivity function for the tracking problem. Okay, so the function that we are considering is the complementary sensitivity function, and we look what happens if there are variations in the process. So what you need to do is take the derivative of this one with respect to the process. So you'll have this one squared. You take the denominator times the derivative of PC, that's C, minus PC times the derivative of this one over here. And then you divide by, well, the complementary sensitivity function divided by P, and this is what you have over here. Of course, this one will cancel out with this one. Okay, this one will cancel out with this one. This one will cancel out with this one, and this one will cancel out with this one. So we're left with 1 over 1 plus BC, and this is the sensitivity function that we have defined previously. Okay, this is why this function is called the sensitivity function. It's the sensitivity function in closed loop for a tracking problem, but also for a load disturbance rejection problem. You still have to check this. Remember that this sensitivity function is the transfer function from dV to PV, but also the transfer function from SP to epsilon, the control error. Notice that the sensitivity in closed loop, sensitivity to process variations, will be low where the loop gain is high. So in frequency ranges where the loop gain is high, typically in the low frequency range, and this is what we'll investigate now. We will now investigate this sensitivity function in the frequency domain, and in this case P and C are complex quantities. This sometimes comes as a surprise to some students, but it shouldn't. Remember that Z is the exponential of TSS. This is the link between the Z variable and the S variable. If you're working on the J omega axis in continuous time, this means that you're working on the unit circle in the Z domain. Here omega TS, where omega is expressed in radians per second, TS is expressed in seconds, so the discrete frequency that lives in the interval minus pi, we'll often consider it in the interval 0 to pi. Well, this is expressed in radians. Well, what is often done is that in a frequency range that goes from the 0 frequency to some frequency omega 0, we want a small enough modulus of S. So what we impose is that the sensitivity function in the Bode diagram, in the top part of the Bode diagram, is smaller than some epsilon in this frequency range. And of course this epsilon is chosen much smaller than 1. Remember that 1 is the sensitivity in open loop. So in closed loop, by setting these specifications, we can have a sensitivity in this frequency range that is much smaller than 1. And what we have to do is to make the denominator over here sufficiently large, and this can be achieved by introducing an integrator in the loop gain P times C. If you have an integrator in either the process or the controller, you have a pole in either the process or the controller in Z is equal to 1. Remember here that Z is the exponential of J omega, right? So this means that at the 0 frequency over here, you will have a sensitivity that will be 0, because this one will tend to infinity. In such a case, so when there is an integrator in the loop, there is no sensitivity at all to variations in P at the 0 frequency, so in steady state. A small value of the sensitivity function in a given frequency range, and typically it will be in the low frequencies, omega to 0 to some omega 0, means that the effect of process perturbation is negligible in tracking and load disturbance behavior. This is just what we have seen. Okay, the sensitivity function is really the sensitivity of the transfer function PC over 1 plus PC when P is varying, or the sensitivity of this transfer function when P is varying. Okay, and if you impose a small sensitivity in this frequency range, well, the effect of process variations on both tracking and load disturbance will be small in that frequency range. But you also know that the sensitivity function 1 over 1 plus PC is the transfer function from output disturbances dV to PV. So if S of Z, the sensitivity function, is small in this frequency range, this means that in this same frequency range the output disturbances will be attenuated very well. If we look at the top part of the Bode diagram associated with this sensitivity function, so we look at the gain or the module. Here it's expressed in dB. Well, you can kind of see here omega here is the discrete frequency, so I could put omega over here, right? And you look up to pi. Remember that omega, the discrete frequency, is related to the analog frequency by this relation. So if you have pi over here, the analog frequency is pi over Ts, so that's the Nyquist frequency. So what is usually done as far as the sensitivity function is concerned is that in the low frequency region you tend to push here so that it becomes as small as possible in the low frequency region. And as we have said, this will be positive as far as disturbance rejection is concerned. This is output disturbance rejection, and this will make the closed loop system, okay, the one that you have in the tracking problem, but also the one that you have in the load disturbance problem. So load disturbances are disturbances at the input. Well, these transfer functions will become insensitive to variations in the process in this frequency range where you make S as small as possible. Of course, you would like to have the sensitivity small over all frequencies, but we will see next that this is not possible in practice. Well, it is possible to show that the integral from 0 frequency to the Nyquist frequency of the log of the modulus of the sensitivity function is given by this expression over here, and the pi here are the poles of the loop gain P times C that are outside the unit circle. So we'll make things simple. We will assume here that there are no poles in the loop gain that are outside the unit circle, and what happens then is that if this is the case, well, this is simply equal to 0. Well, this means that if you look at this log of the sensitivity function in a linear scale for omega, and what you have here on the y-axis is the log of the modulus of S, right? And what you will see is that if you express this in a logarithmic scale, because you have the log over here, you will have 0 over here, and that, well, you will have something like this. And the area that you have over here is exactly equal to the area that you have over here, and this is because this integral from 0 to omega n of the log here of the modulus of S is equal to 0. Right, so in a diagram with a linear scale, this area corresponds to this area. Remember again that this is the case where we do not have any poles outside the unit circle for the loop gain, but this means that we cannot make the sensitivity function small at all frequencies, because if you reduce the sensitivity by pushing over here, what we'll have is that, well, this part here will have to increase, because we know that the area in red corresponds to the area in blue, and this is called the waterbed effect. There is a nice picture coming from Gunther Stein, and I've borrowed it. You can see the reference over here that illustrates this. If you try to make the sensitivity function small at some regions, what will happen is that you will make it larger in some other frequency ranges. In the next two slides, we look at the sensitivity for a tracking problem if we take into account the sensor dynamics. Obviously, the ideal sensor dynamics here is 1 over all frequencies, but in practice this will not be the case. If you consider the tracking problem and you compute the transfer function from the reference input, the set point, to the output, this is the transfer function that we will obtain. And now we can have a look at the sensitivity to changes in the sensor dynamics. So here we consider a tracking problem and we want to see, well, the sensitivity with respect to the sensor dynamics. We consider the following transfer function, PC over 1 plus P PSC, and here this is really the dynamics of the sensor. So if you compute the sensitivity to sensor dynamics, it's just a matter of applying the definition and go through the calculations. I will leave them, but you can rewrite this sensitivity as follows. Remember that at low frequencies you will make sure that, well, the loop gain is large. So at those low frequencies we have here a sensitivity to sensor dynamics that is -1. So there is a high sensitivity to variations in the sensor dynamics. It is therefore crucial to have a sensor of good quality with sufficient robustness against environmental changes, typically for a sensor changes in the temperature.